Okay, so this is our first bit then on dynamics of a particle. So let's take a wee look at what we're talking about. So if the forces acting on a particle are not in equilibrium, then acceleration takes place. The dynamics of the particle depend on Newton's laws of motion. So law 1 states that the particle will remain at rest or continue to move at a constant velocity in a straight line unless acted upon by an external force. Plenty of chat about that in time to come, but effectively if I take something and I push it, it will keep going that way unless it's stopped. It'll just keep sliding forever if I start to push it unless it's stopped by something else. The reason the calculator doesn't go obviously then is kind of friction's acting this way to kind of stop it coming back, but that's the way number 1 works. Law 2 is the resultant force applied to a particle is proportional to the mass and the acceleration produced, and we use F equals ma then to represent that. So force equals mass times acceleration. We use that an awful lot. And then law 3, every action has an equal and opposite reaction. And note, an object at rest or moving with constant velocity is regarded to be in equilibrium. So if it's in equilibrium, it's either at rest, the thing's not moving, or it's moving with constant velocity, it's not accelerating. And in that case, everything then is in equilibrium. So that would suggest that in this particular case, this one says this is at rest. The numbers are really, really straightforward here in all these questions. But it's a concept, so they're the tough bit to get your head around. So you really need to concentrate on those in as we do it. So this one's at rest, and you'll hear me say this a lot. If it's at rest, or that means it's in equilibrium, that means everything going this way equals everything going this way. And everything going this way equals everything going this way. So in this particular case, very straightforward really. We're going to have A is going that way, and that equals then 30 newtons, the 10 then plus the 20. And then B, let's do everything kind of going. So B is going down, you can see the arrow, and the arrows that are going up, there are the 30 and the 20. So 50 newtons. Again, it's a concept, obviously the sums are very, very easy. And let's take a look at an example 2. A car of mass 600 kilograms is travelling along a straight horizontal road with an acceleration of 2. The engine is exerting a forward force of magnitude 1500 newtons. Find the magnitude of the resistance it is experiencing. So here is my road. Here's my car. I tend to keep things nice and simple looking. Not the fanciest car you've ever seen. And it's 600 kilograms. It's an acceleration of 2. The way we normally do that is to do a double arrow with a 2 there. The forward force is 1500. That's the engine force, and we want to work out then the resistance that it's experiencing, so we're going to call that then R. If it was not accelerating, it would be in equilibrium. Everything going this way would equal everything going this way, so R would equal 1500. But there is acceleration, and in that case we're going to use then F equals ma. I always start with the right hand side. It makes me feel better about myself because it's easier. The mass is 600, the acceleration is 2, and then this F here stands for any force which affects the direction of the acceleration. So this is 1500 going this way, and then the R is going the other way. So this is going to be 1500 take away R. So tidying up then, 1500 take away R equals 1200. So in this particular case then R must equal 300 newtons. Okay. Example 3. A bucket of concrete of mass 40 kilograms is hoisted up the side of a building. Find the force in the lifting rope called the tension if the bucket accelerates at 0.25 meters per second. So the diagram here then. Here is my bucket. 40 kilograms. If it's hanging in the air, that means then there is 40 times gravity acting down. So that's 40g acting down that way. Pulling it up, it's been hoisted up, and we're going to call that tension. So the string is effectively the force, the rope that's pulling it up. The tension in that string is the force that's pulling that up. If it was in equilibrium, everything going this way equals everything going this way. The tension in this string would be 40g, or 40 times 9.8. But it's accelerating up. We do our double arrow, 0.25, and we can then work out our tension. F equals ma. to the right hand side, 40 times 0.25. And then what do we have acting? What's the positive direction is this, so it's going to be T, take away 40G equals 40 times 0.25 T, take away, so we do 40 times 9.8 here, which I think gives 392, I'll check it in a wee second, and then 40 times 0.25 will be going to give us 10, so tension then is 402. Let me just check that, in case I didn't believe myself. What are we doing? 40 times 9.8. Yeah, 392. So the tension in the string, or the tension in the rope, must be 402, and that's the force then that it's pulling up with. Of course, this has to be bigger than for 392. If it's 392 going down, this has to be bigger if there's going to be acceleration. If it was in equilibrium, this would be 392, and this would be 392 as well. A lift is accelerating upwards at 1.5 meters per second squared. A child of mass 30 kilograms is standing in the lift, treating the child as a particle. Find the force between the child and the floor of the lift. This is a tough one. I think this is quite awkward to get your head around. So here is my floor of the lift. Here's my child. We're going for accuracy here. So what's happening now with this child? There is 30G acting down this way, and there is an R, which is their normal reaction. Again, we chatted about this before. If you're sitting in your seat, the reason my 100 kilograms of weight isn't, sorry, 100 kilograms of mass isn't firing down through the seat is the seat is holding me in place, so it's pushing up with the same force. That's why I'm in equilibrium. But this here is going up. And my double arrow then this is 1.5. So we're going to use F equals ma. Again, this is a much tougher one, harder to get your head around, but hopefully you can see what's going on. The acceleration is here, so it's going to then be R, take away 30G. I should have done the right hand side first, shouldn't I? 30 times 1.5. 30 times 1.5 is 45, then plus the 30G, and then the R is 339 newtons. Just a wee comment about that before we do move on. So as you sit in this seat, the seat you're sitting in currently, you can probably feel the weight of your bottom on the seat and the seat holding you in place. In the same way, I'm sure you've all experienced in the lift, whenever it goes up you kind of feel heavier, you feel like you're kind of being pushed down into the floor very slightly, and that's why where that R is, that's your normal reaction. The normal reaction needs to be bigger than the 30G acting down, otherwise the child then kind of won't go up, and that's where it goes. So that's the normal reaction, is the force without the acceleration. When a body lies on the surface of the earth, it is under the influence of gravity. The force on the body due to gravity caused to exert a force on the ground, and the normal reaction reacts in the opposite direction, causing the resultant force on the body to be 0. Finally then, example 5, let's take a wee look at it. A particle of mass 4 kilograms is initially at rest at the origin 0 on a smooth horizontal plane. Remember, our word smooth means there's no friction. We'll come on to friction later on in the unit. It is acted upon by two forces, that's 4i plus 5j. So 4i is 4 going across this way and 5 going up, so we'll be going at that angle there. And then 2i minus 3j is 2 going across and 3 going down, so it's kind of going that direction there. Find the resultant of the two forces. Very straightforward one for us. Our resultant is then P plus Q, 4i and 2i, 6i. Remember, this is a vector, so we underline it. 5 take away 3 plus 2j newtons. That's the resultant force then of the two forces P and Q. The package moves from 0 with acceleration ai plus bj. Find the values of a and b. So what's happening? The package is 4 kilograms. There's the force acting on it, that's the F, and we know our M, and this is in our A. So we're going to set this up then. F equals MA. That's a vector. That's a vector. So 6i plus 2j equals 4 upon AI plus BJ. 4A is 6. Do you see where I'm getting that from? I hope so. So that means you can see this okay. A then must be 1.5. And then 4B is the same as a 2. That's the J component there. So B then must be equal to 1/2. Find the values of A and B, so we've found those. That means the acceleration in this particular case is 1.5A plus 1/2. Sorry, 1.5I plus 1/2 J. After 4 seconds, the package is at point A. Find the displacement vector OA. So that's going to be UVAS now. So let's take a look and see if we can suss this out. See if we can get the relevant information that we need. U, V, A, S, and T. U is 0 because it's initially at rest. V, we don't know. A, we've just worked out. It is V over 2. That's the same as 1.5. I plus 1/2 J. Displacement is what we're looking for. And the time then is 4 seconds. So we can do it. We have U, A, and T, and we want S. So I'm going to use S equals UT plus 1/2 AT squared. Luckily our S is, so our U is 0, so that bit disappears. And we have 1/2 upon 3 over 2I plus 1/2 J. And then that's all upon 4 squared. So let's do some sums. 4 squared is 16. If I times that by 1/2, I get 8. So we need to times both the things in here by 8. So if it times this by 8, I'll use 24 over 2, which is going to be 12. I times this in by 8 plus 4J. And that's my displacement then after the 4 seconds. So it's at 12I plus 4J.